So good morning to everyone. Good morning. Okay. So still students are less. Okay. So as you people know, today we are going to solve some of the questions related to solid state. Okay. So related to solid state. First chapter in part 1 chemistry. Okay. So which we have already discussed in the theory class. Fine. Now when it comes to solid state, before going to solve the questions, we'll have a brief discussion about the concepts which and all it is there in the solid state. Right. So now when it comes to first one, so that's where we have discussed about amorphous and crystalline solids. Amorphous and crystalline solids. Right? So we have discussed that one, as glass is the example for amorphous solids, and for crystalline solids we have many like NaCl crystals or diamond. They are all example for crystalline solids. Okay. Now when it comes to crystalline solids, so once again we have different category. So that's where we have the molecular solids, which we have discussed, where molecules will be present in forming the crystal structure. Therefore they are called as molecular solids. So in that we have non-polar, right? Non-polar molecular solids, then polar molecular solids, and hydrogen bonded molecular solids. So we have different categories. So non-polar, polar and hydrogen bonded molecular solid. So based on the intermolecular interaction, they have given the classification in case of the molecular solids. And all of us we know that they will be having low melting point, very low melting point. Okay. So that's where we have the molecular solids. Now when it comes to next category, in crystalline solids only, we have metallic solids. We have the metallic solids like iron rod and all. They are the example for metallic solids. Then we have the ionic solids, which is an example for ionic solid is NaCl. Same way we have the covalent solids, right? So where covalent bonds will be there, which are also called as macro solids. Fine. So that's where we have the crystalline solids, types of crystalline solids. Next we have discussed about the unit cells. In case of the unit cell, or what you mean by unit cell, it is the structural unit of a crystal. It is the structural unit of a crystal. 1 minute. It is the structural unit of a crystal. Now when it comes to this particular solid, means unit cells, we have different types. We have primitive unit cell, then we have body centered unit cell, then we have the amorphous, then we have the body centered, then we have the face centered. Somehow I wrote amorphous. So that's where we have the three major types. Along with that we have end centered. That's where we have different types of unit cells. Fine. So now along with that you should know about the coordination number. You should know about the coordination number. Now when it comes to coordination number, on this you can expect the question in your competitive exams. So what do you mean by coordination number? Coordination number is nothing but with how many atoms a particular atom or molecule is going to interact in a crystal structure. So that is called as coordination number. Now number of unit cells, all of us will know. So we can make a chart. When it comes to body centered cube, so where coordination number will be? What will be the coordination number here? In a body centered cube, it will be 8. In a body centered cube, coordination number will be 8. So number of atoms, you can write it down. Number of atoms in a unit cell, in this case, in this type of packing, number of atoms in a unit cell, it will be 2, which we have to calculate, which we have calculated also, right? So that's where number of atoms will be 2. So you can write down this particular chart. So now when it comes to FCC type of packing, coordination number will be 12 and number of atoms in a unit cell will be 4. Okay, same way we have the CCP. We have the CCP, cuboidal closed packing. So where coordination number will be once again 12 and number of atoms will be once again 4. Okay, and the last one, that's where we have hexagonal closed packing. So coordination number will be 12 and number of atoms will be 6. So this chart is bit important because on this you can expect the question. All of you have understood? So that's where we have different types of packing. Where body centered packing, it will be having coordination number as 8, number of atoms in unit cell will be 2. Now when it comes to rest of the one, it is related to FCC or CCP or hexagonal closed packing, coordination number will be 12 and the number of atoms in a unit cell will be 4 and in SCP it will be 6. Remember this. In SCP it will be coordination number will be 6. Fine? All of you have understood? I am talking about number of atoms in a unit cell in a packed, different types of packing. Okay? So that's what that chart talks about. Now once we have discussed about that one, then we have wards. Right? Then we have the wards. So what is that wards? We have the empty spaces between the atoms in a crystal structure, right? So we have 2 types. So tetrahedral wards, we have the tetrahedral wards and octahedral wards. We have the tetrahedral wards and octahedral wards. And all of us we know octahedral wards will be 2n and tetrahedral wards will be, octahedral wards will be n and tetrahedral wards will be 2n. Right? So that's equation, relation is very important where number of atoms in a packed structure will be n and then octahedral wards will also become n and tetrahedral wards will become 2n, double to that of the number of atoms. This is related to wards and remember those relation between number of atoms, octahedral wards and tetrahedral wards. You can expect the question. Okay? Now, next after this wards, we have the packing efficiency. Then we have the packing efficiency. Right? Now when it comes to packing efficiency, all of us will know FCC or SCP or CCP. All of them, they will go for 74% approximately. 74% of packing, right? And when it comes to body centered cuboidal packing or BCC, so it will be 68%. It will be 68%. Then next one is simple cubic packing. So simple cubic packing, it will be somewhere around 52%. Somewhere around 52%. So all these things you should be remembering. This is with related to packing efficiency. And please remember, as I was reducing this particular percentage, this one, during that time I told you have to remember relation between edge length and radius of the atoms in these different types of packing. That one you should remember. Fine? Or if you are getting confused, then you can derive that particular percentage. During that time you will find out the relation between A and R. Sometimes they have asked the question based on those things also. Okay? So that is related to packing efficiency. Next one is crystal defects. Next one is crystal defects. So that's where we have the Frankel defect and Schottky defect. That's where we have the Frankel and Schottky defect, especially related to ionic solids. It is especially related to ionic solid. When it comes to Frankel defect, there is no change in the density, right? But when it comes to Schottky defect, there is a decrease in the density. Fine. So that's where we have the interstitial defect and vacancy defect. Okay. So that's where we have the Frankel and Schottky defect. Then we have impurity defect. Doping, right? Impurity defect. When it comes to semiconductors, we are going to dope that one with different group element. Group 14 will be doped with group 15 or group 13. So if you are doping group 14 elements with group 13 elements, then it will result into P type of semiconductors, right? Then it will result into P type. So if you are doping with group 15 elements, then it will result into N type of semiconductors. So positive and negative. So positive hole and here electrons which are negatively charged. So that's where we have the impurity defect, which is done purposefully. Okay. Then we have the metal excess defect. Then we have the metal excess defect. So which can be done when sodium chloride is heated in the presence of sodium. So then it will lead to metal excess defect, where we have discussed about F center, Farben-Genter center, right? So that's where we have the colors, where free electrons will be there, which will lead to the colors, right? Now, as we have discussed, potassium chloride, it will be violet in color. And when it comes to lithium chloride, it can be pink in color, or sodium chloride, which can be yellowish color. So that's where we have the colors, that is due to the F centers present in those crystal structure, which is due to the metal excess defect. Fine, all of you have understood. Then we have the magnetic properties. So where we have paramagnetism, then diamagnetism, then ferrimagnetism. Try to remember the examples. Then anti-ferrimagnetism, then finally we have the ferromagnetism. Finally we have the ferromagnetism. Okay, so finally we have the anti-ferromagnetism. Finally we have the ferromagnetism. So that means all of us, we know that a ferromagnetic substance can be converted into a magnet, right? Nickel and iron, they are the example for ferromagnetic type of substance. But when it comes to ferrimagnetism, they will be having slight affinity, or they will be having less affinity towards the magnetic field. But when it comes to paramagnetism and ferrimagnetism, they are a bit comparable because they have the less affinity. But diamagnetism, no, they don't show the magnetic property. But ferromagnetism, a paramagnetic substance can be converted into ferromagnetic substance under provided condition, like iron and nickel. They can be converted into a permanent magnet. So that's why they are called as ferromagnetic substance. So try to remember this one. And when it comes to ferrites, to which category it belongs to? Ferrites. It can be magnesium ferrite or whatever it is. To which category ferrites belongs to? It belongs to ferrimagnetism, right? So that's where you should remember the examples from these types, okay na? And the last one is related to density of the unit cells. Okay, anyway, so all these things, whenever we'll be solving the questions, we are going to discuss that one, okay? So whenever we are solving the question. So any doubts in these things, or shall we start? Okay, now first one. First question here is amorphous solids. Amorphous solids. First one, possess sharp melting point. I will be writing it as MP. Possess different physical properties. I will write it as PP. Physical properties, melting point, physical properties. Then are supercooled liquid, or supercooled liquids. Then final one is possess crystal symmetry. Possess crystal symmetry. So please remember, I have taken the question from different competitive exams, which is also including NEET, CET and IIT questions. Okay, but it will be from not only from those exams, I have taken even from other exams also. Okay, so which is that one? Banu Kumar is writing option C. So here R in the sense, I use this short form. R means ARE, are supercooled liquids. Okay, all of you are going with option C. Yes, when it comes to amorphous solids, they are called as supercooled liquids, right? So due to that, they don't have the proper crystal structure. Due to that liquid character in them, so they don't have the proper crystal structure. So due to that liquid character, they don't have the sharp physical properties. They don't have proper physical properties, and they don't have sharp melting point. They don't have sharp melting point. So that's where we have the anisotropic and isotropic character. So what do you mean by isotropic character?
Different direction.
So isotropic character means due to the proper crystal structure, they will have the different properties at different angles when it comes to scattering of light. So that's where it is called as anisotropic property. Isotropic means they have the same property at different angles with related to diffraction of light. Right? Isotropic character is related to amorphous solids. Anisotropic character is related to crystalline solids. What do you mean by long range order and short range order? Long range order is with respect to crystalline solids, and short range order is with respect to amorphous solids. All these things you should remember. So that's where the first question, option C, will be the answer. Next, second question. unit cell of NaCl crystal is A, body centered cube. Option B, simple cubic or simple cube. Option C, face centered cube, FCC. Then option D, hexagonal HCP, that is hexagonal closed packed type of structure. So unit cell of NaCl crystal is So that's where we have body centered cube, simple cube, FCC type or HCP type. Hexagonal closed cube, FCC, that is face centered cube, simple cube and body centered cube. Okay, Banu Kumar is telling option C. Okay. Now, when it comes to NaCl, please remember, since it is a ionic solid, it should have equal number of Na plus Cl minus. And please remember, since it is ionic solid, one ion will be of larger, another ion will be of smaller. Right? So where Cl minus will be here and Na plus will be here. Cations will be of smaller size and anions will be of larger size. Okay? So due to that, if you consider in the corner we have the chloride. In the edge center we will be having Na plus. Or we can have Na plus and at the center we can have Cl minus. So what I mean to tell here is, although the speciality of NaCl crystal structure is, although it is having a cuboidal structure, cubic structure, where on the corner it will be having ions, at the face also it will be having ions. That is because when I am connecting these atoms or ions which are present here, I can have this type of one where another ion will be present here. So what I mean to tell here is, corner, center of the edge and along with the face center, everywhere it will be like this, it will be arranged. Here also it will be there, here also it will be there, here also it will be there, here also, like that NaCl crystal structure will be arranged. So therefore I can split one particular cube into multiple cubes. In case of the NaCl, I can split one particular cube into a multiple cube. So that's where I can see here. Right? So like that I will be having multiple cubes within the cube. Right? So therefore when it comes to NaCl, it will have the FCC type of structure, but when it comes to number of atoms in a unit cell, it will follow the SCP type of crystal structure. That is, coordination number will be 6. That is because difference in the ionic radius, large difference in the ionic, slight difference in the ionic radius. That's where we have the crystal structure that is related to NaCl. So try to remember that. And ionic radii ratio, that is radius of cation and radius of anion. So that's where R plus divided by R minus. And when it comes to NaCl, it will be ranging from 0.2 to 0.4. Somewhere in this particular region it will come. Radius ratio of NaCl. Anyway, we are going to discuss these things, radius ratio also, when we are discussing question related to that. This is not there in your board syllabus, but sometimes they are asked within the competitive exams. Okay? So radius ratio. That's where we have the NaCl crystal structure. Okay? All of you have understood? Hmm? Now, one thing you should remember that magnesium, zinc and all, they will go with SCP type of packing. Those metals, they will go with the SCP type of packing. But when it comes to FCC, it can be NaCl or it can be copper. These are some of the molecules or metals which will show FCC type of packing. All of you have understood? So try to remember about the NaCl. Next one. Question number 3. Coordination number. Coordination number. Coordination number of unit cell is 12. Its cell is coordination number of crystal structure. It should be not unit cell. Coordination number of crystal structure is 12. It's a cell A, primitive, B, simple cubic, C, face center, and D, body center. Body center. Can anyone? Face centered or body centered? So question is coordination number of a crystal structure is 12 or in a crystal structure is 12. Its unit cell will be primitive type or simple cubic type, face centered type or body centered type. So Bhanu Kumar, okay. Bhanu Kumar is giving the answer. Okay, very good. So that's where we have the face centered. Right? That's where we have the face centered. Yes. In the beginning only I had given one chart, right? So in that chart it is there. So coordination number whenever it is 12, it should be related to unit cell where it will be FCC type. Where it will be FCC type. Okay, so this is related to that particular chart. So therefore, try to practice those charts, and you can find that chart in any of the competitive examples. In the beginning, they will be giving explanation, right? So in that you can find that one. Okay, we'll move to the next one. Question number 4. AB close packed structure. AB close packed structure represents A, simple cube, B, BCC, C, FCC, and D, SCP. So AB type of packing. This one we have discussed already in the theory part. Okay, Bhanu Kumar is writing D. Oh, very fast, very good. Okay, na? So AB close packed structure, as Bhanu Kumar has written, it should be SCP. If it is ABC type, if it is ABC type, then it will lead to the FCC or even BCC. But if it is simple cubic, it will be AAA type. It will be AAA type. That's where we have the AB close packed structure. It will lead to the formation of SCP. If it is ABC, it can be FCC or BCC. And when it comes to simple cube, it will be AAA type. Bhanu Kumar. Okay, CCP means cuboidal close packing. Cuboidal close packing. It will be same as that of the BCC. It will be same as that of the BCC. That means what I mean to tell you, it will be resulted due to ABC type. It will be resulted due to ABC and ABC type. Okay. So that's where we have the different types of layer arrangement, which will lead to the formation of different types of crystal structure. Okay. Whether I am clear? And normally when it comes to packing efficiency, SCP or CCP, they will be of equal when it comes to packing efficiency. Fine. So all of us, we know it is somewhere around 74%, both of them, CCP also, SCP also. All of you have understood? Cuboidal close packing. Okay na? Any doubts? Bhanukumar, whether I am clear? Okay. Fine. We will move to the next one. So next question is germanium doped with gallium is an example of A, intrinsic semiconductor, B, N-type semiconductor, and C, donor type of semiconductor, next one is D, P type of semiconductor. Okay. So which one? Which should be the answer among these? Okay, Bhanukumar is very fast. Bhanukumar is passing out second year student, right? Whether I am right? Bhanukumar, who is passing out second year student, if I remember. Okay, very good. So answer should be P type, because gallium, yes, expected Banu, yes. So when it comes to P type of semiconductors, that is because gallium belongs to group 13. Gallium belongs to group 13. That is after aluminium it is there. Okay. So as we know, boron family, that is group 13 elements, if you add it to the germanium, which is a group 14 element, naturally since gallium is having 3 valence electron because group 13, and germanium is having 4 valence electron because of group 14, it will lead to the formation of P type of semiconductors. It will lead to the formation of P type of semiconductors. All of you have understood? Intrinsic semiconductor, it cannot be possible because intrinsic means without doping, by itself it should have the conducting capacity, right? Where selenium or germanium should not be mixed with or doped with any of the other element. Then it will lead to intrinsic. Here we are talking about doping. So therefore it cannot be the answer. And the type also cannot be the answer. So that is not at all related, and this is P type of semiconductors. Okay. So that is because gallium belongs to group 13 element. After aluminium it is there. Okay na? So that's where we have question number 5. So we will move to question number 6. Which one of the following which one of the following, which one of the following defects, which one of the following defects in the crystal, which one of the following defects in the crystals lower its density, lower its density. Okay, so first one, Frankel defect. First one is Frankel defect. B, F centers, F centers. C, Schottky defect, Schottky defect. And D, interstitial defect, interstitial defect. Anyone? Okay, so it is Schottky defect, no doubt. Because in Frankel defect, it is also called as dislocation defect, right? So where in original place it will make the vacancy, but in where the movement has been taken place, it will lead to the interstitial defect. Both the type we can observe in Frankel, but altogether there is no loss of any of the element. So therefore density will not be changed. So that is the speciality of the Frankel defect. And this one we know. Can anyone tell me F center formation, which is a defect, crystal defect, whether it will lead to increase in the density or decrease in the density? Formation of F centers, whether it will lead to increase in the density or decrease in the density. Formation of F center is a defect. What will happen?
Increase of this side.
No, what will happen to the overall, that crystal structure? Anyone? Okay, Manvit is telling it will increase. Yes, naturally it should increase because you are adding extra sodium. If I take NaCl, you are adding extra sodium. So due to that, what is happening? Chlorine is moving, right? The place of chlorine ion or chloride is taken by the electrons. So that's where there is no loss of any chloride. Still it has moved to the periphery where metals were there, but its place has been taken by electrons. But chloride is not lost. Okay, it's still present with the crystal structure. Okay, present in the crystal, but there is additional sodium which has taken place. So naturally it will lead to increase in the density. That is F center, formation of F center. So Schottky defect, equal amount of ions will be lost. So there is a decrease in the density. And all of us we know that interstitial defect is nothing but where there will be movement of ions from its original place to another place. There is no question of decrease or increase in the density or the rate. But at original place from where that atom has been moved, it will lead to decrease in the density, and to which place that particular atom has moved, in that region it will going to increase in the density. That's where we have the interstitial defect. All of you have understood? Next one, question number 7. In a cubic closed packing, in a CCP of spheres in a three dimension, the coordination number of each sphere, is I have written coordination number as CN. A 6, B 9, C 3 and D 12. Already I have given the chart while explaining the concept. What should be the answer? Yes, Banu, you are right. It should be D 12. Coordination number in CCP it will be 12. That's what I have given the chart. Even SCP it will be 12. Please remember, once again I will tell, when it comes to CCP, SCP and FCC. So in all this case, in a crystal structure it will be 12. In a crystal structure it will be 12 coordination number. But when it comes to atoms in a unit cell, in their respective packing, all of them they are packing only. I am not talking about the unit cell. So don't get confused with FCC. It is not a unit cell. So when I am talking about FCC, coordination number will be, number of atoms in a unit cell will be 4. Even here it will be 4. But when it comes to SCP it will be 6. So coordination number in a crystal is different. Number of atoms in a unit cell is different. Okay na? So that's where we have the FCC, CCP which will be having number of atoms in a unit cell as 4. When it comes to SCP, number of atom in a unit cell will be 6. But when it comes to all together as a crystal, each atom or element will be having interaction with 11 other elements. So therefore coordination number will be 12. So it will be, total coordination number will be 12. It will be having interaction with 12. So that's where we have the coordination number and number of atoms in a unit cell. Don't forget these things. You can expect questions on this. Okay? So that's where we have the number of atoms in a unit cell is different. Coordination number is different. Okay? And if I take body centered cube packing, body centered packing, then the coordination number in a crystal structure will be 8. But the number of atoms in a unit cell is 2. So that's what you should remember. So 8, 12, it is common. But when it comes to number of atoms in a unit cell, it will be 2, 4 and 6. When it comes to SCP, it will be 6. Fine? All of you have understood? So these things you can remember. Many times they have asked questions related to this. So we will move to next question. That is question number 8. A vacant space or the vacant space in BCC unit cell is, in BCC unit cell is option A 32%, option B 10%, option C 23% and option D 46%. So Mayank has given the answer. Anyone else? Yes, Bam, you are also right. Even Mayank was right. It should be 32%. That is because when it comes to BCC type, packing efficiency is 68%. That means 68 part among the 100 is packed. Rest of them is vacant space. Therefore, 100 minus 68 it will be 32. Right? So if I take CCP or FCC type, then vacant space will be 23. So it will be, for example, I have 74% approximately. I have 74%. So naturally 100 minus 74. How much? Anyone? It will be 26%. So why we are making it as percentage? Because we are making it 100 minus. So anything related to 100 we will consider it as percentage, right? Same thing if you go for this one, simple packing, simple cubic packing. So where it will be approximately 52%. So then 100 minus 52, it will be vacant space. How much? It will be 48%. So that's where I have the percent vacant space. That's where I have the percent vacant space for the different type of packing. Percent vacant space for the different type of packing. Okay? So that's where we have the vacant space in BCC unit cell should be 32. Option A. That is because 100 minus 68 it will be 32. Okay? We'll move to the next one. Next one is a compound is formed by, listen, write it, you can write it down. A compound is formed by, elements A and B. Element A and B. This crystallizes in the cubic structure. This crystallizes in the cubic structure where A atoms are at the corners and B atoms are at the body center. The simplest formula of the compound is option A, A6B, option B, A8, B4, option C, AB6, and option D, A. Anyone? A compound is formed by two elements, that is A and B, where A will be occupying the corners and B will be occupying the center of the cube. Banu has already given the answer. It should be option D, AB. That is because any atoms if they are at the corner, that means one will be belongs to that particular unit cell, right? And anything which is at the center of the cube, that will also become 1. That means A and B, the ratio is 1:1. So therefore simplest formula of the compound will be AB. Okay? Rest of the options cannot be the answer. Okay? So that's where we have option D as the answer for this particular question. We'll move to the next one. Question number 10. The edge length of the unit cell of NaCl unit cell of NaCl, crystal lattice. Crystal lattice is 552 picometer. If the ionic radius, if the ionic radius of sodium ion is 95 picometer, what is the ionic radius of chloride ion? What is the ionic radius of chloride ion? What is the ionic radius of chloride ion? Okay, saying that option A 368 picometer, option B 190 picometer, option C 276 picometer, and option D 181 picometer. About sodium chloride crystal I have told, so based on that we should solve. Okay, Bhanu is very fast, very good. Okay, so Rakshita, whether you had given the answer for this or earlier question, I think. Okay, Bhanu has given the answer as option D. Right? Okay. So it is absolutely correct. So please remember, as I have told, for NaCl, there will be presence of ion at the corner, there will be presence of ion at the center of the edge, and there will be ions present at the corner. So based on this, I can see here. So there is R1. So this is R2, and this is also R2, and this is once again R1. All of you will agree? By considering R1 as the radius of chloride, R1 as the radius of chloride. So R2 is the radius of sodium. Okay? So by considering that, we can tell that in a NaCl crystal structure, edge length will be equal to 2 into R1 plus R2, because both are twice it is there. So R1 is also twice, R2 is also twice. 2 into R1 plus R2. Right? So now in that case they have given the edge length, that is 552 picometer. So 552 picometer as edge length. Then they have given one of the ionic radius, right? So 2 into 95 picometer plus R2. So if I solve this one, definitely I am going to get answer as 181 picometer. Calculate. Plus 2R2. So it will be 552 picometer is equal to 190 plus 2R2. Right? So then 2R2 is equal to 552 minus 190. How much it will be? 552 minus 190. 552 362. It will be 362 R2. Therefore, R2 is equal to 362 divided by 2. I think it's correct. It will be 181 only. Okay? So it will be 181 picometer. How we got this formula? Have you understood? All of you have understood how we have got this formula. That is because we have the corner and the edge of the center of the edge. There will be presence of another ion. So therefore we can write it as 2 into R1 plus R2. Okay? So try to solve this type of problem they have asked. Any doubts in this? Okay. So in that case, we'll move to the next one. That is question number 11. Question number 11. Atoms of elements A form SCP lattice, and those of element B occupy the 2/3 of tetrahedral wards. 2/3 of tetrahedral wards. The formula of the compound is option A, A4 B3, option B AB2, option C AB3, and option D A3 B4. Can anyone? A3 B4. They have given it will form SCP lattice. They have told it will form SCP lattice. Okay, Banu, absolutely correct. It should be A3, B4, option D. Okay? So now, when it comes to this particular thing, all of us we know that since they are talking about SCP, each unit cell should have the 6 atoms. In that case, how many tetrahedral wards? So therefore, it should be 2n. So therefore, tetrahedral wards will be equal to 12. It will be 6, right? So 2n, n is equal to 6. It should be 12. So therefore 2n it should be equal to 12. So therefore we can tell that formula of the compound can be, that means A is equal to, it should be 6. It should be 6. Now what about B? B should be 2/3 of the tetrahedral wards, right? That means 2/3 into 12. 2/3 into 12. So that means it is equal to 8. It is nothing but is equal to 8. We can write it as A6 B8. A6 B8. So any option is there? A6 B8? Nothing is there. So further solve it. So we can write it as A3 B4. A3 B4. All of you have understood? Once again, you should remember what is the number of atoms in a unit cell in SCP. That was 6. So it is 6. N is equal to 6 means tetrahedral word is 2n. That means 12. So therefore, A is equal to 6, B is equal to 2/3 of the tetrahedral bonds. So therefore, it will be 8. So A6B8. If you have A6B8 as one of the option instead of this, if that would have been there, you should have gone for that. But since it is not there, further simplify it, we will be having A3B4. All of you have understood? Any doubts in this? Anyway, I will stop here. Tomorrow we are going to continue with the next set of questions. Any doubts? If you have any doubts, you can ask. Okay. Okay then. So I will stop here. So tomorrow we are going to continue and we will solve some more questions on solid state. Okay. Thank you. Take care.